Welcome back, everyone. In the first part of the session, we explored the fundamentals of weather forecasting, from busting myths to understanding how observational data is collected and assimilated into models. Now, we are ready to dive deeper into the science that powers modern weather prediction. We are delighted to have you join us for another exciting session of the Vismay Vigyana YouTube webinar series, a science outreach initiative under the Jigyasa program by CSIR 4th Paradigm Institute, Bengaluru. Today's webinar is the continuation of the topic Weather Forecasting, Myths, Science and the Future, and will be delivered by a leading expert in the field, Dr. Vivekananda Hazra, an atmospheric scientist. He currently serves as a scientist at CSIR 4PI Bengaluru and an assistant professor at the Academy of Scientific and Innovative Research, ACSIR. In this second part of the webinar, Dr. Vivekananda Hazra will take us through some of the core components of numerical weather forecasting and how they work together to produce accurate and timely predictions. He'll be covering topics like types of weather forecasting, coordinate systems, parameterization, the role of AI and ML, and the future of forecasting. So, let's get ready to explore how weather prediction is evolving and what the next decade might look like for science, technology, and society. Please join me in welcoming back Dr. Vivekananda Hazra for part 2 of his talk.
Thanks, Rina. I welcome you all again. So far we have covered about some myths and data collection procedures, data collection instruments, and how these data are being fed into data assimilation system to create a real state of the atmosphere, the current state of the atmosphere, which is called analysis. Now we'll be looking into how we use these numerical weather prediction models to predict the weather. So weather forecasting, conventional weather forecasting, actually has three components. Apart from AI/ML driven forecasting, we have three types of forecasting system. One is synoptic weather forecasting, second is statistical, and third is numerical weather prediction. Numerical weather prediction has another component, that is finite difference, which is called grid models, and another is spectral models. So we'll be discussing mostly this finite difference model, that is grid models. But in spectral model, data are considered as continuous wave function, and so some examples are like ECMWF model, like European Center for Medium Range Weather Forecasting model, and we have unified model where they use spectral model. And there, so we don't dive in detail within this spectral model. So let's focus on finite difference model. Finite difference also has like two components, hydrostatic and non-hydrostatic. And this finite difference, actually you'll be knowing of unified model or WRF or hurricane WRF, the HWRF. These are all finite difference model where all the equations are solved in a particular grid point. So synoptic weather forecasting, this is an atmosphere. The atmosphere at a particular location is known through an instant, like a set of meteorological variables like temperature, rainfall, wind speed, and direction and pressure. These are called synoptic charts. So using the observation recorded, surface and upper air chart are prepared. Then inference can be drawn by seeing the charts, by using previous charts as well as current chart. So in addition to another like charts, satellite pictures also an important component of this synoptic weather forecasting, but it has some issues. In initial actually older days we used to predict weather like this using this particular method, but it has some serious flaws, not flaws, some issues, like selection of the past analogous situation is based on experience and memory of the person who is looking at this particular charts. So this would be involving some kind of human errors, measurement errors, or kind of stuffs. But with the advent of advancing in computation, so we'd be using computer rather than human interferences. So then comes statistical weather forecasting. These methods are like use past records for weather data, and it relies on an assumption that the future will be the repetition of the past events or past weather events. And these methods are mostly used in long range prediction, climate forecasting, and generally the techniques are based on multiple regression or auto regressive integrated moving average, RMA. So they use for prediction of Indian monsoon rainfall. This actually works well for monsoon rainfall. However, RMA model fails on meteorological subdivision wise, since this is not a region specific thing. So, and apart from this also, model needs to be tested and verified, validated regularly. So this also has some like issues. So better we would be going for numerical weather prediction, which is the most advanced version of weather prediction. So this is whether NWP model is a computer program that produces meteorological informations for a particular region and for like future time steps. And the model is nothing but a set of equations which are known as primitive equations, which are used to predict the future state of the atmosphere. These equations along the ideal gas law are used to evolve with density, pressure, potential temperature as scalar fields, and the velocity of wind as a vector field of the atmosphere through time. Now NWP consists of like this model consists of like several equations which are called governing equations. Generally it uses the fundamental equations of like conservation of mass for both air and water. Second, conservation of momentum, which is derived by Newton's second law, that is horizontal equation of motion as well as vertical equation of motions. Third is conservation of energy, which we get by thermodynamics, like first law of thermodynamics. Last, not last, but equation of state and some water vapor equations. And it is to be noted that all the equations are non-linear partial differential equations. So using these equations, we will be knowing some basic physics about the fluid flow, about the convection, about turbulence, radiation, microphysics, and ice growth. So here is the example of one-dimensional advection equation. If you see the first term, that is the partial differential equation, which is del v del t equals to minus v of del v del x. So v and del v del x both are dependent variables. So we have a non-linear situation here. So we use this. We generally convert this PDE into a difference equation. Here, like Vik plus 1 minus Vik divided by delta t equals to minus Vik of like I plus 1k minus I minus 1k divided by 2 delta x. So where I is position and k is the time. So by which we can get Vik plus 1. And so here also we are neglecting some higher order terms, which also leads to some kind of uncertainty generation, or you can say error generation. And now comes coordinate system. So where we have to use vertical, like top of the atmosphere, as a coordinate system. So the initially generally it was like first initially used as a pressure coordinate system, where pressure lines are considered as coordinate systems. And it was easy because there are some like handful of like useness about this particular coordinate system, but it has some issues. Like first thing is that pressure changes over the time over places, and coordinate lines generally cut the topography. So that's why we generally don't prefer. Then comes sigma coordinate system, where the equation is sigma equals to p by ps, which is p pressure and ps is surface pressure. So we'll be having like sigma values 1 to 0. So 1 will be at surface and 0 will be at the top of the atmosphere. So this is actually a terrain following coordinate we can get. But the one issue with this particular coordinate system is that it is like it unable to resolve horizontal pressure gradient forces for a like sharp elevation. So but mostly our advanced models are use eta coordinate system or hybrid coordinate system, which in the lower troposphere we use terrain following coordinate system, but in the upper atmosphere we use pressure coordinate system. So let us see like how we generally predict the weather using models, and how do you calculate these particular equations. So now come to like Earth. Okay, so on Earth we'll be going for India. So let us assume a particular region. For our case, we will take India. And now what will we do? We just create some mesh around this particular region, like this, some grid boxes. Then we will fix a domain. Unless if you want to calculate or you can to simulate some cyclone or some heavy rainfall event or thunderstorm, then we don't need to run our model for the entire globe. So we'll be fixing for a region only, like regional area only. We call it regional models. So in regional model, this would be the structure of the grids, where each grid point will be solving this basic primitive equations. And this type of coordinates I'm just showing for your reference. This is a Arakawa C grid, but we have other type of grids also, like Arakawa A grid, Arakawa B grid. So this is how we calculate these equations, this partial differential equation, non-linear PDEs for this each grid boxes. Now one important issue with modeling like NWP is how do you resolve this subgrid scale processes which actually occurs within a particular grid box, because we will be calculating our equations in this grid boxes, all these grid points, but a lot thing happens within the smallest grid box, and model must approximate the effects of the subgrid scale on the resolved grid scale. So we need to know what is going within that particular. There may be one pond, there may be some other vegetation. So these effects needs to be taken into account while giving a forecast, or at least calculate, because this each grid point is the average value of a particular grid box, this red dots that you're showing. But we need to somehow need to know what is going in between, and some fundamental parameterization schemes, we call it parameterization. These fundamental parameterization schemes are like land surface, cloud microphysics, which actually helps in rainfall generation. Then turbulent diffusion, we call it planetary boundary layer, where exchange of fluxes occurs, mass momentum exchanges of mass and momentum occurs from surface to upper troposphere. So we call it planetary boundary layer. Then we have orographic drag and radiation, like incoming radiation as well as outgoing radiation. So this is a case study, not a case study. I just prepared it for this particular webinar, just to show you that how we generally do the modeling. So this is a sample image of a particular model output that I performed, which is showing for a funny cyclone, where I have taken a small region over Bay of Bengal, and I have tried to simulate it from one time to another time, and through which we are just seeing here some radar reflectivity plots and as well as the tracks. So now what we'll do, we'll just validate these tracks with our observed tracks, like which IMD provides. So then we can get to know like in what way my model is getting failure, or my model is having any issues or not, because I have already my observation data sets of this particular cyclone and I want to validate it. So by doing this, I can get to know that how close I can go towards observation. So now we'll be looking at the future, and future means it is the augmentation of artificial intelligence as well as machine learning in weather forecasting. So currently there's like physics enabled some AI tools are there, which actually helps NWP models to enhance their prediction capabilities. And generally nowadays ML is being used for model bias correction or parameterization. But now you'll see that deep learning for short-term models like Google MetNet, and they use satellite data or radar data to predict the rain, and at a very high resolution, like 1 to 2 kilometers, and with higher accuracy. So in our traditional NWP models, it will take hours to simulate the entire scenario, or like it will give around like 10 days forecast. It will take actually at least hours. But in nowcasting using AIML, you can get it within seconds. So this is one advantage that AIML can give us. Thirdly, data assimilation system. Artificial intelligence can help some noisy data sets, which we get, as I already discussed, we get some data from satellites and radars. So it actually helps to correct those data and optimize the initial conditions for NWP. And also in ensemble forecasting, DL helps us, and it can give us some probabilistic approaches like scenarios. I didn't include ensemble forecasting. Ensemble forecasting is like a way of, like, we generally part of the initial conditions to get different types of simulations. So if we don't do anything, it will call be as deterministic model. But if we perturb some initial conditions, then we'll have ensemble model. And ensemble model can be done in other way, like if we can use multiple physics, because as I already discussed about parameterization schemes, we have so many parameterization schemes. So we can like opt different schemes. So that's how we can also get some like different models, or not different models, different runs. Thirdly, we can use different boundary conditions also. So by this three way, we can generate ensemble prediction, and nowadays using ML also, we can generate probabilistic forecasts. Third and fourth, this global models. AI ML nowadays can act as a global model also, like Pangu weather or GraphCast. You probably be knowing that there is a model called GraphCast, which actually matches the NWP accuracy at 1 to 7 days. And running cost for this models are like minutes, not even hours. So within minute you will get a 7 days forecast. So that's how AI is helping nowadays. But limitations, obviously there will be limitations, where it is still complementary to NWP, traditional NWP. It cannot be a full replacement of traditional NWP. This also struggles with rare or extreme events datasets, like extreme events, because we don't have that much of data to train. Another most important aspect is this black box term. So we don't know what is going in between that DL model. So this is another concern for using machine learning. But what can we achieve using AI/ML? So in future, hyperlocal or high resolution predictions. Nowadays, if we see for global models, it will go maximum up to like 6 kilometer, and for regional model, you can go up to 1 kilometer or maybe sub kilometer also. But using AI/ML, you can go even more deep. Like you can and AI models can be used by IoT sensors, or so it will help us predict the street level rain or wind or temperature. So that's how high resolution you can go for. Second is seamless integration, so you can have options for like choosing days or minutes or years. So this is called seamless, that can be also achieved. And then extreme predictions. So federated learning can be used like for using global data to focus unprecedented floods or heat waves. And we can use AI for like cyclone predictions, intensification, or droughts even weeks in advance. And another thing is that climate resilience, AI powered like solutions like rapid climate impact projections for policymakers in terms of like crop yields or like flood risks. Then computation efficiency is the one of the important aspect, because here AI actually cuts the cost of supercomputing by 99%, because Penguin there it uses 1% energy of traditional NWP. So there's a much you can save much money. And why it matters actually, how AI can help, and if we can increase our forecasting capabilities using AI/ML in future. Because by WMO, that is World Meteorological Organization, has said that weather forecasting could save at least 300 billion US dollar annually by 2030, if we just play tactically by disaster prevention or optimized agriculture or even energy management. So I actually did not discuss about any errors of the model, because weather focus still have some like issues or limitations despite of use of modern technology and improved techniques. But from data collection to assimilation and forecasting, there are several errors are involved. So that's how errors are getting generated, and that's why we get some sort of erroneous forecast. But if we compare with like 50 or 60 years of like prediction accuracies, it has been improved drastically. And weather forecasting is complex and not always accurate, especially for days in days further in the future, because weather prediction can be chaotic and unpredictable. Weather is actually totally chaotic in nature, so it is a kind of predicting the unpredictables. So thank you for your attention. If you have some queries, you can ask.
Thank you, Dr. Vivekananda Hazra, for that fascinating overview of the world of weather forecasting. We have a few questions. I request Dr. Hazra to please answer them. So the first question is, how do disaster management teams or farmers use different types of forecast in practice?
Disaster management teams or farmers, they actually get the weather inputs from district magistrates.
Okay.
Where actually our authorized organizations like IMD, they generally issue weather bulletins as well as some advisories to district magistrates. Then it's their job to disseminate further to ground level. And if something is coming like cyclone or something, then we directly contact those NDRF or something, those teams directly. So that's how we actually disseminate the informations from higher authority to lower
authority. Okay, sir. Yeah. So one more question is, are there situations where AI models have outperformed the physical models in forecasting?
It's there, but being a conventional modeler, I would not I would not say that, but yeah, because nowadays if you see GraphCast and some other tools which are actually helping, because in computation, if you see for traditional NWP, it will take at least hours to run globally. Then if you have to run regional model, then you have to take some output from the global model. So if you ask about in forecast mode, if you want to forecast weather, then the computational efficiency would be much higher for AIML models. So that's how it can be achieved, but it has some like limitations also, because it entirely depends on the training data sets, and for that model has to be trained properly regularly, and that's a tedious job. And to catch some some other phenomena which are like cloudburst or even cyclone prediction or thunderstorm, uh, yeah, we can use, because nowadays actually physics informed models are also being used in machine learning. It can save time, yeah, for the time computation time purpose, I can say, yeah, it can save time, but it cannot fully replace conventional models, that is for sure.
Okay, sir. Yeah, thank you. So, how is India adopting to the AI in its forecasting systems, especially for monsoon prediction?
Yeah, monsoon prediction also, AIML is being used actually in data assimilation. We are using machine learnings in forecasting. If you see like only you want to ask like whether AIML can fully like now fully means it can give you some idea, because we are working on a particular issue that we have to predict the monsoonal forecast, like monsoonal rainfall, by machine learning, but using so we can get some tentative idea, but things are going on actually. Machine learning is like drastically improving, and this is a hot topic right now.
Yeah.
So I'm not using machine learning specifically for my simulations. I take help from like machine learning guys who would help me in my some issues which is required for my model, but I don't believe that it will be replaceable
By the
traditional methods.
Yeah. So as this Jigyasa initiative is for the students, I would like to ask a question regarding the career path. So if a student wants to pursue a career in this weather forecasting, so what will be the career path? Like how can a student go ahead?
Yeah, students actually you have to have a basic degree. If we don't provide undergraduate degrees,
Okay.
we only provide postgraduate degrees, like masters or like MTech like MSc or masters, MTech. That's the only option which is followed by a PhD. So masters you can do in IITs. We have Indian Institute of Science here, and NIT, some NITs. So the process of getting into these institutes are through GATE. So or mostly GATE, or some institute may take some entrance exam, but through GATE you have to appear for some interview, then they will select you. So this is for MTech. Then you have to pursue PhD. If you want to be in this particular field, you have to do PhD. So PhD is being offered by various institutes. Like we have leading institutes like Indian Institute of Tropical Meteorology, we have IITs, we have NIT and ISC. Some private universities are also there. But to be in this particular field, this is a interdisciplinary subject. So people may come from math background, people may come from physics background, may come from chemistry or even engineering. So civil engineering, mechanical engineering. So the common platform is they have to pursue masters first, and masters have been provided by various institutes. So and then after doing PhD, you have to go for postdoc. There are several options are there for postdoctorate positions, and you can join some other institute as a scientist also, like assistant professor or something. So that's how your career will go.
Yeah, thank you, sir. As we come to the close of today's enlightening session, we extend a heartfelt thanks to Dr. Vivekananda Hazra for taking us on this fascinating journey through the science, technology, and the future of weather forecasting. From understanding the basics of data assimilation and model dynamics to exploring the potential of artificial intelligence and machine learning in predicting extreme weather, today's webinar has truly deepened our appreciation for the complexity and importance of atmospheric science. We would also like to sincerely thank each one of you in the audience, students, teachers, and enthusiasts for your active participation, thoughtful questions, and continued curiosity. Your engagement is what makes the Jigyasa webinar series meaningful and impactful. We hope this session has not only answered your questions but also sparked new ones and perhaps even inspired some of you to explore careers in science, weather modeling, or environmental research. Stay connected with us on the CSIR 4PI YouTube channel, and we look forward to seeing you again in future webinars. Until then, stay curious, stay inspired, and keep exploring the wonders of science. Thank you and have a wonderful day.